All right, so now what we want to do is we're going to end up deriving an explicit differencing scheme that will calculate the time varying temperature profile. So basically what this is going to do, this next expression that we're going to write out, is basically it's going to allow us to calculate how the temperature evolves over our bar. So I'm going to just make a line right here. So we're going to have our temperature bar right here with our different slices. And we already said earlier that our n in this case will be our time increment, and then our j, this will be the position along the temperature bar. So we'll have, this will be our position. And we're going to just rewrite the thermal diffusivity equation. So we're going to have the derivative over the derivative temperature over time, and then we have times the thermal diffusivity, and then we have the dt over dx, and this will be squared. And then we're going to multiply that again, dt over dx again, just so we can show that it's going to be two derivatives. So basically what we want to write is, so our temperature profile, T, at some position J, this will be Tj, and then at the next time increment, this will basically be able to for us to calculate what it's going to be at the next time increment. So this is coming from this right here. And then that will be minus the temperature at some position at the previous time increment over the change in temperature. And then we will have the thermal diffusivity alpha, and then we'll have times the temperature. We'll have time. This will be on this side of the equation right here, so we need to do this twice. So we have the temperature J plus at the next position at some time increment, and then that will be minus the temperature J at the time increment, and this will be over delta x. So this will be the one of the derivatives, dx, or the change in temperature over dx, change in position. And then we want to take the derivative again, so we're going to just subtract, and then we'll have tj at some time increment minus, let's take the derivative for this again, so we have tj at some time increment minus tj minus 1 at some time increment over delta x. And then since this will be the second derivative, we're going to divide this all by delta x. Now what we want to do is we can just do some algebra. So now what we can do is basically, this is delta t right here. So basically now what we can do is we can combine this left side. So we have our alpha. So we have our alpha, and then we'll have our tj n plus 1. And then we're going to have our alpha times our tj plus 1 n minus our 2 times the temperature at some middle node at n, and then we'll have minus t at some time increment, and then at the previous position j minus 1. And then we can from this side we can multiply delta t. And then we can also, what we can also do is we can, we'll then divide by, if we combine these, we'll have delta, this is actually supposed to be delta x, and then we'll have delta x squared if we combine those two. And then we can add our temperature at the original node, j, to this expression. So that gives us the temperature at the next time increment at our j position. That'll not be n plus 1, that'll just be tj to the n. And the last thing that we want to do in order to get our temperature profile, in order to make this a little bit more simple, is so we will now have our tj at some time increment at the next time increment. This will be when we vary the heats in our temperature bar, we're going to be able to calculate how the temperature profile evolves from this next time increment. So then we're going to call alpha times delta t over delta x squared. We're going to call that r. So we're going to have we're going to have alpha, or we're going to have tj at some time increment times, or plus, sorry, this is plus r, and then we just copy this rest of this down, tj plus 1 over n minus 2 tj n minus tj n, or j minus 1, which is the previous position in our temperature bar, and then we can go ahead and multiply that by r. In this case, our r would be alpha delta t over delta x squared. So that just simplifies our expression a little bit. But this is our final expression for our what we're looking for, and this will be basically the explicit difference scheme in order for us to calculate the time varying temperature profile. So basically, if we look at our bar, when we change, say we change the heat right here and heat right here, when we increase the heat, then the heat's going to diffuse throughout our bar for each side, and basically it's going to be able to for us to calculate the temperatures at a certain node at the next time position. And that is we're going to end up coding this out. And this expression, I'll say right now, this expression we're going to code it out, and there are certain stability constraints for r in this expression right here, in which we're going to notice. So eventually we're going to have to, we're basically going to have to rearrange this expression in order for us to get no stability constraints, but we're going to calculate that later. Okay, so now what we're going to do is we're going to implement this in Python. So for number 3, we can see that we're going to end up plotting our results, and we're going to show how this equation can be stable, but with certain values of r, we're also going to show how it can be unstable. So we're going to just go off, and we're going to start out, since we're going to be making plots, we're going to end up importing numpy as np. And since we're going to be also making plots, we can just go ahead and import our plotly stuff. So we're going to have from plotly dot subplots, and then we're going to import make subplots. I believe that should be it. And then we're going to have, since we need our we have to import our graph objects, so we're going to have from plotly dot graph objects, from plotly dot graph objects, and then we'll put this as geo, and then this actually needs to be import, not from, import. So we're going to import plotly graph object, and then the geos for abbreviation, and then we're going to have import plotly.io, and then we're going to import this as PO for abbreviation. And then if we want a dark graph, which just looks a little better, we'll have pio.templates default, and this will be equals to our plotly dark. So plotly, this will be our plotly dark template. Okay, so we can shift enter that. Those are just will be our imports in order we need to make our plots. And now we can define our original variables which we need. So we know that our thermal diffusivity, alpha, which we can call, we know that this is going to be equal to, if we go back, we know our alpha, our thermal diffusivity, is going to be 1 meters per second squared, squared per second, I mean. And that's going to be 1, so this will be our thermal diffusivity. And then we also need the length of our length of our bar, and we're just going to call this we can call this nx, and x is for like the position, so we know that's going to be 50 meters. And then we have the number of time increments we want, which is going to be the n, and our nx is technically going to be the certain j's that we have, and we'll just call nt, and we'll say that we can say this is 1,000 at first. And then what else do we need? We need how many position spatial steps we have, and we can go back and we say that that is going to be 1 meter. So we're going to go ahead and put that in. We can just call this our delta x, or we can just call this dx, and we'll say that's going to be 1, and we do not need the bit length. And then we also need the our delta t, which we can just go ahead and say that this is equal to 0.1 at first. And then we also have from our equation, we have our r value, which we said was just a relationship between our alpha, our thermal diffusivity, and our delta T divided by our delta X squared. So we can say that's alpha divided by, alpha times our delta T dt, and then that's divided by dx squared. And then now what we need to do is specify our original temperatures and what the temperatures are going to be at the ends of our bar. So we can do that by saying our initial temperature. We can say that this will be the NP full. In this our temperature profile array, we first need the shape of our bar, which is going to be 50, which is our NX. And then we're going to have our fill value, which we are the initial temperature. We'll say this is 20. And now we can specify our temperature at the, so we actually, what we can first do, shift enter that, and we can first just say, what is our, shift enter, we can say, what is our T, just so we can kind of see it. So right now, this is what our array looks like, 50 time steps, or 50, that's the shape of our bar, between 1 meter each. So right now it's all at 20, but what we can do is specify the first temperature and specify the last temperature, since it's going to be, we're going to calculate, see what the temperature profile is as the temperatures go in. And now we have, so we'll have T0, and that will be the temperature in the first index. We can say that this can be equal to 50 Celsius, I guess. And then we'll say that the temperature at the last index, so since we're going to the back, we're going to do -1 from Python indexing, and we'll say that this is equal to 80. So now when we shift into that and shift into that, we can see that our temperature profile has changed a little bit. So our first temperature at the first end will be 50, and our at the last end will be 80. And that's from these two right here. And so now what we want to do is we're going to go off and plot this out. Okay, so now we can go plot this out. So first we can start, we can just go fig equals make subplots, and then that'll start, and we're going to have just rows equal 1, and we're also going to have our columns equal 1. So we're going to say rows equal 1 and columns equal 1. And then we can say we want to make a scatter, well actually what we first need is we need to specify what our x values are going to be. So we can go off and we're just going to put it up here. We can say our x values, these will be in the range, so we'll have their a range. And then we're going to, or np, we have to have np.arange, np.arange. And then we're going to say these x values are in where we're going to start. So we're going to have our length of our bar, we're going to have that's going to be nx. And then we're going to have nx, and we're going to multiply that by each spatial step of our bar. So we have, that will be our dx. And these will be our, we can say this will be our positions that we want, x positions of our bar. So we'll say those will be our positions. And then now what we can do to go off and plot it out is we can just go ahead and add a scatter plot, I guess. Oh, did not mean to do that. We can go off and add a scatter plot. So we can say fig.add and then underscore scatter. And then we can say our x values, that is going to be equal to our x, which we just specified up here. And then our y values, we'll say those are going to be equal to our y values, those will be equal to our temperature, or T, our temperature array. And then we can just name this, we'll just call it the initial. So this will be the initial line of our temperature profile. And then, so now to create our scatter, basically what we need to do is, now we need to iterate through our time increments of our temperature profile. So we can do, to do that, we're going to go do like a for loop. So we'll do the for I in range, and our range in range. And then in this case, our range will be from 1, starting from 1, and then it will go all the way to our time increments. Right now we have specified as 1,000, so it'll be nt, and then since Python indexing starts from 0, we'll do +1. And then now what we need to do is iterate through our equation from the or iterate through our equation which we just wrote. So to do that, we just need to go off, and so if we look at it, we can see that our equation right here, we're going to have a time increment at a certain node j, original node, and then we're going to have, that's going to equal the next time increment. So that's what we're calculating. But we first need our initial time, our initial position at the first time increment, and then we're going to add r, which is our alpha, or thermal diffusivity, times our delta t over our delta x squared. And then we're going to multiply our temperature at the next position at the certain time increment minus 2 times our temperature at the time at our original node, which is t jn, and then we're going to subtract back from the last position. So we're going to have to do j minus 1 at a time increment. So we can go off and code that out in our array, or in our for loop. So we're going to iterate through this. So what we're going to have is, first we're going to have the temperature. So if we go back, we're going to have the temperature at the position at the next time increment. So the temperature of the first position at the next time increment, we're going to have t and 1, -1. And then that will equal to our temperature, which we're going to iterate through at 1, :-1. And then we're going to add that to our r. So we're going to have plus r, and then that's going to be times our, if we go back to the equation, we'll have plus times the t value at the next position. So this will be the second position, and then at the time increment, and then minus 2 times what we have here, right here, and then minus the temperature at the previous position. So that's going to be the temperature back. We're going to go back there. So to code this out, we're going to go, so our temperature at the second position, so we're going to have 2, and then 2, and that will be 2 at the second position. And then we're going to subtract 2 times the temperature at the internal node, which we have is 1, and then -1. So we go back. That's taking out those last values, and then we add the temperature at we go back a position at our time increment. So that would be t at 0, :-2. So I think that looks right. So this basically will show us our equation, and I believe this equation is right. And so now we can go off and I guess we can see what our plot looks like. So we can go fig dot show, and we'll just go off and shift enter that. I think I need a colon here. Okay, so we can see that we have that initial lines at first. But what we want to do, so it doesn't iterate through too many times, is basically what we need to do is we need to because since it's going to be iterating through over 1,000 times, we don't want, it's going to show like way too many lines. So basically what we want to do is we can basically use this modulo function in our for loop, and basically what this is going to do is only plot the ones that basically plot the ones only that are a multiple of it's only going to plot the ones that are a multiple of 10 if we do it this way. So we'll have if I modulo which is what this percentage is, 100, and if that equals 0, so basically if it's a multiple of 10, and then we'll have our fig, and then add scatter, or scatter plot, and then we'll say our x is equal to x, and then our y is equal to t. And then our mode in this case we can just say is lines, so we can see our lines. And then we'll name this. We can just name this instead of naming it the same as initial. We can name it our temperatures we're going to iterate through. So we can just do like the f string. So we'll name f string, and that's going to be we'll just call it I. So we'll iterate through which one we're iterating through. Okay, so now we can shift enter that and see what happens. Looks like I need a colon there, not a semicolon. Put a semicolon again. Shift enter that. Okay, so we can see here that we have these temperature values, and this is kind of like what's showing like what our temperature profile would look like. But we're not done just yet. So basically, this actually isn't stable. Right now, we have our R value as what it looks like right now. But if we go off and let's say we'll change our time step, we can kind of see how this might change. So we can say our R, when our time step goes to 0.5, okay, so we can see it's still a solution. When we change our time anchor into 0.5, we can say it's still our solution. But when we go off and say we make our time steps 2,000, and change that again, okay, so it still works. Everything's still converging correctly. But if we look a little bit further, we can see that if we change this past 0.5, watch this. So say it's 0.6. Look at that. That is not stable at all. We have 1 times 10 to the 289th power. That is not stable. So basically is we can see if we want to go, if we want to see where this is going to stabilize out, we can just make it a little bit less than that. So we can do 0.51. Okay, look, still not stable. We still have 4 times 10 to the 30th. That's still a huge number, and we can see it's not stable now. So if we want to get a little bit less, so we'll go 0.501. Okay, we can see it's starting to stabilize out a little bit, but you can see these little ridges right here that still makes it not stable. So if we go 0.502, look at that. Definitely not stable. And I think it's kind of cool to see these graphs. They're kind of little fun little instability graphs that we can look at. I mean, it's kind of cool. But basically our equations are all right. This way of doing this finite differencing, we did it the wrong way. So basically, we can just see a little bit more. If we want to, we can see it a little bit better if we reduce this to like say 20. We can see the instability is a little bit better. Okay, so it looks like it's not too bad right there. But if we change this like back to like 0.51, the instability comes right back. See, just does not work out. So if we change it to let's say 0.503. Still, okay, it's a little bit less, it's a little bit more stable. Okay, now I'm going to actually change this back to 50, which is what we want in our problem, at 2,000 time steps. But look at this. That's just 8 million. That's just not stable whatsoever. So basically what we want to do is we can kind of see from these. So if we go 0.5001, you can see, okay, it's pretty stable at 5.5001. But basically you can kind of see that if it goes past 0.5, if our R value goes past 0.5, it's not going to be stable. So basically we can show the stability and instability. So if we go back to 0.5 as our time increment, we can see it's stable again. But if we go back here to our notes, what we're going to want to do next is we're going to end up doing a Crank-Nicholson finite differencing, in which actually solves this instability issue, in which we got from using the equation this way. So that's where we're going to be headed next.